Okay, so let us summarize block diagram algebra. So blocks are used as operators. Let us consider the multiplication block. So a block acts upon the input and gives an output. Now this can be represented as the output equal to the block P acting upon the input U. Now since this is a multiplication block, uh, the action of P on U is nothing but the multiplication of U by a number P. So hence the output is P into the input U. Uh, Now consider an integral block. Here the action of the P can be represented as the output equal to action of P on U. Now this is an integral block, hence the output is integral of U of t, that is the action of P is integration of U with respect to time. Now the blocks are generally used in cascade, that is in series parallel connections. So let us consider this example and consider two cases. Firstly, these two blocks are multiplication blocks, and then we'll consider both of them to be integration blocks. Now considering multiplication operators, we can write the output, the extreme output y, as action of P on y1, where y1 is an intermediate signal. Now y1 is the action of k on u, hence the overall output can be written as action of P on action of P on k of u, that is P of k of u. Now this would be a general relation irrespective of the type of the block. Now comes the assumption of multiplication operator. So k of u, so P of k of u. So P, since P is a multiplication operator, so P of and the quantity inside it is nothing but the multiplication of P with the quantity inside. So P into k of u. Now similarly we can open k of u, since k is also a multiplication block, so P times k times u. So overall this entire system is y equal to P into k into u. That is, we can assume this as overall multiplication block of constant pk. Now since this is a as I said, this is a general expression, is irrespective of block, for both of them being the integral operator, this won't change. So y equal to P acting upon k acting upon u. Now since P is integral operator, so this is nothing but integration of k of u dt. Now again k is a integral operation, so this is integral of integral u dt dt. Now let us consider another example of feedback interconnection, a simple example. So here we'll consider both of these to be multiplication blocks. So our objective is to find y in terms of r. So this implies that E is r minus the input coming from this branch. So E is nothing but r minus the input from this branch, and the input of this branch is the h acting upon y. Since this is a feedback connection, h picks up y, acts on it, and gives information to this combination block. Hence E is r minus h acting upon y, and y is g acting upon E. Hence this can be written as r minus h of g of E. Now since this term is familiar, like we have used it here for multiplication block, this opens up to pku, hence it would open up to hgu, where h and g are constants of these multiplication blocks, and on rearranging we can separate E in terms of r. Now to get y, we use the relation that y is g acting upon E, and g being a multiplication block gives ge. So y is g by 1 plus hg times r. Hence we get the output in terms of the input and the multiplication blocks, which are in feedback interconnection. Now I'll give a problem for you to solve. This is a practical feedback system where we consider the disturbance, the sensor noise acting in a feedback system. So the objective again is to find y in terms of the r. So I'll want you to solve this. I'll give the answer. This is an important example, since we'll build upon this in terms of reference tracking, noise rejection and disturbance rejection. So the answer gives some terms which would be important in further analysis. So this is the map from R to Y, this is the map from N to Y, and this is the map from D to Y. So we'll further consider these results in the further summary.